So welcome to Rishabh. So Rishabh's going to be talking about the object avoidance changes in ArduPilot. There's been a lot of work in object avoidance over the last year. And so Rishabh has been leading the charge on that. And over to you, Rishabh.
Just a second, let me just share my screen.
Sure.
Right. Am I visible?
Yep, looking good.
Right. Okay. So thank you so much, Andrew, for the introduction, and congratulations to the last speaker. That was an amazing, really interesting talk. So moving on with obstacle avoidance. Right. So not a lot of you actually know about me. I'm a fairly recent addition to ArduPilot. So just a little introduction about me. I'm an undergrad student, fairly young, 22 years old, and I study at BITS Pilani, India. It's a famous university here in India. And the first PR I made was a little, almost 1.5 years back in June 2019. And actually the very first experience I had with ArduPilot was back in my first year in college, when I saw a couple of seniors who were flying with those APM 2.6 boards, and just it was just amazing to see how well those even those old copters flew. So I decided, let's just gather a team of people and make ArduPilot supported copters just for fun. So we got around, we're a bunch of really enthusiastic people, and we got about 100 people to sign up, and all of us actually made more than 100 quadcopters and flew it, and none of us actually knew how to fly them. So it was all a huge scramble with all of us flying in stabilized mode and none of us actually knowing what to do. And we broke about 50 propellers that day. So that was my introduction with flying. And of course, the first PR came a few years later. And subsequently, I started preparing for Google Summer of Code. For those of you who don't know what Google Summer of Code is a 3-month program. Now it has been shrunk to about half, but it's a 3-month program that Google sponsors for students like myself to interact with open source organizations and work with them, work with the industry leaders in, but only in open source organizations, much like ArduPilot. And I was subsequently selected as a Google Summer of Code student at ArduPilot, and was tasked with improving the obstacle avoidance features that we support. So obstacle avoidance was a recent addition. It's not as old as most features in ArduPilot is. It's something that is quite recent. So my task was to figure out. Actually, Randy did most of the work of figuring out what was there to be improved and what were the bugs. But my job was to fix them. Ever since then, I have been an active tester, an active developer, and most recently, this just March ending, I was also selected to be part of the dev team, one of the newest members of the ArduPilot dev team. So thanks for that. Just an outline of what can you expect from this talk today. So today I am just going to give you an overview of the entire setup of how we gather data from the sensors, and how do we process it, how do we store it on board, and then how do these algorithms actually use these data. And so about half the presentation is actually just videos. It's like a movie. The first half might be a bit boring about gathering the data, but the rest of the half is just purely videos, and should be fun. So obstacle avoidance is of majorly two types in ArduPilot, and that's because we have the autonomous flying modes, and we have the not we have the semi-autonomous flying modes, or the manual flying modes, where the user is taking control themselves. So for the autonomous modes like the auto or guided mode, we already know where the flight is heading to, right? We already know the general direction where the vehicle wants to go to. So we can plan a path, we can avoid obstacles, we can plan around the obstacles, we can do all that kind of stuff. But with manual modes, we really don't know where the user wants the vehicle to go. You're going straight 1 minute, and the next second you turn right, and you can do whatever you want. So there's no just to mention that there is no way you can plan ahead. So there are two different algorithms that we use to deal with this. So the first part of the presentation is going to be explaining you what simple avoidance is, which is basically done in manual modes. And the next part would be on bendy ruler and Dijkstra, which is done in autonomous modes, which are basically part of a path planning suite. Um, the if you see under the manual mode section, just a second. Yeah, if you see under the manual mode section, I have two different algorithms, which is one is simple avoidance and one is ping pong method. I don't think it's named ping pong method, but that's just how we refer to it. I think Randy named it this. And simple avoidance basically works by reducing velocity in the direction of an obstacle. So if the vehicle is approaching an obstacle, and we have calculated that it's definitely going to break the margin around an obstacle that the user has set, then it just reduces the velocity. Whereas the ping pong method, or which does not really require GPS, it's done mostly in altitude hold modes. That one actually works on angles. So if we are pitched 15 degrees forward and we are approaching an obstacle, it reduces that pitch to say 10 degrees or -5, -10 degrees, so that we go away from it. So the proximity library, right? So many people actually, especially in the discussion forums and while talking about avoidance with me, they kind of confuse it with the rangefinder library. The rangefinder library is not the same as the proximity library. The rangefinder library is used by plane, it is used by copter, it is used by rover, but the proximity library is only used by copter and rover. The rangefinder library basically takes care of those 1D lidars that only provide point distances to just one orientation. Whereas proximity library actually handles lidars like you see on the bottom right corner, the rotating RP lidar, where you have 2D 2D data that is being fed directly into ArduPilot, and these data can be 10-20,000 separate data points a minute, and the proximity library actually does all this calculation to help us store that data. Right. So the 10,000, 20,000 different points that are possibly entering into ArduPilot, we can't store. I mean, we'd love to store all those points, but it's not physically possible, right? For us to store that and for us to process it. So what the proximity library does is it makes a boundary, it makes a filter, or you can call it a filter, that reduces those points so that we have an easier time in storing and processing it. So this is what the proximity library does. You can imagine, imagine yourself to be the quadcopter right here, and imagine yourself in a flexible hula hoop, holding a flexible hula hoop. So this is what we call the mini fence, and this mini fence is 8-sided. So we could have 100 different obstacles approaching. So each face, each of the side is called a sector. So we could have 100 different obstacles on each sector. So 100 obstacles here, 100 obstacles here, 1,000 obstacles everywhere all along these faces. But we only pick out the whatever is at the least distance. So whichever is the closest in this region. So maybe we have obstacle here which is 5 meters away, an obstacle here which is 10 meters away. But we only pick out the 5-meter one because it is at the closest in this sector. So basically the 10, 20 different 10, 20,000 different points that I was talking about earlier, they are reduced to 8 points around the vehicle. And so when there are no obstacles available, if the copter is just flying happily and there's nothing in its path, this is how the fence looks. It is at its default state. But as soon as say there's an obstacle that approaches from G side, what we do is we bend that hula hoop or bend that fence, and we make it like this. So you see the obstacle, you see what the situation is, but what the vehicle sees is this right here. And this is what the simple avoidance acts towards. So so if you were the vehicle, in the middle, you're going to look back and see, okay, everything's fine at B, C, and D. But if you look forward, you see, oh no, G is approaching too fast. We must do something about it. So this is how it was done in 2020. Uh, right. So as is visible, this is very much a 2D algorithm, right? So for example, I told you we have a object here at 5 meters, we have an obstacle here at 10 meters. But what happens if obstacle is approaching from the top or the bottom? If it's approaching at 10 degrees pitch, how do you handle that? What if there are three obstacles, each at different pitches but at the same sector? What happens then? So this was not really a problem until very, very recent times, because most of the sensors, like the RP LiDAR that we use, they only gave us 2D data, right? They didn't really uh, we didn't really have the access of 3D points. So why bother with all that excess code and the code that is never going to be used? But now in 2021, we have these fantastic new cameras and the fantastic sensors that have the ability to give us 3D data. So, just to speak a little bit about stereo depth cameras, this is a D4 Intel RealSense D455 right here on the right, and so these incredible devices, they are cheap. They are, I mean, relatively cheap. They are small, lightweight, and they have the power to give immense amount of data in one go. So I'll show you, the sort of data that this thing gives. And just to give you a little idea of how these sensors work, because we have been working quite some time on them. So it very much works like a human eyes. So this is like your left eye, and this is like your right eye. And the very oversimplified way of working is that the left eye and the right eye, both of them see the same point, but of course they're slightly shifted, right? So if you close your left eye, if you close your right eye, the vision is going to be slightly shifted. So it uses this baseline, this distance between these two sensors, and it uses that shift in the image to calculate the depth of the obstacle. It's a very oversimplified explanation, but we can have a chat after the conference if more people are interested in knowing how these sensors work. Apart from that, we also have an incredible RGB camera in the center. So what we can do is that you can run all those ML AI algorithms that classify obstacles, and then you can figure out in camera coordinates, you can figure out u comma v, which is what are the coordinates of, say, a human or a toddler walking across. And then you can figure out what the XYZ, the actual physical coordinates of that body frame coordinate of that obstacle is. So that's why these cameras are fantastic, and these are being these are being made better every day. So up until last year, we only had the D4 35i, which was the best camera that Intel RealSense had, and those gave us 10-meter range. But now we have the D455, which gives us 20 meters range easily. So these are being developed every day, and it's just exciting to see where these are heading. So back when I got these cameras, I did not, have any source on, how good these cameras are, or how do they work. So I created this YouTube video, which has actually become quite famous online now, because a lot of people are, seeing um, how the camera functions, and what is the comparison between the D435 and the D455. This is what you get from the cameras. On the bottom, you see there's the RGB normal camera, like a FPV view, and on the top we have the depth visualization. So the way this visualization works, this is an incredible amount of data, right? So the way this visualization works is that the areas in red, they are the closest to the camera, whereas the areas in blue, they are the most further away. So you see those trees in the background that you can see in the RGB camera, they are visible with the blue background, and the ground, which is very, very close by, that is in red. And what I've done is that I've divided this entire view into a 3x3 cross section. And I have printed down, the minimum, what is the minimum distance of what I can find in this grid. So for example, land is 1.65 meters away. whereas those trees in the background are 14, 15 meters away, as can be seen on the top. So the rest of the videos, they're going to have similar representation, and now you know what these what these values, the red values are, and what this grid is. So yeah, just a static test of how well these cameras function. And this is connected to my laptop, so we are getting about 30, 40 frames a second. It goes as high as 60 or 75, depending on what API you use. If you use C++, it's much faster. If you use their Python API, it's much slower. But the point being that it's just incredible about how much data that we are able to gather from these sensors. Right. So this brings us to the question, now, as you saw, this hula hoop kind of thing that we do, this mini fence thing that we did in 2020, this is no longer sufficient, right? We need something that if a user tells you, there's an obstacle at 2 meters up, 3 meters to the right, and 5 meters away, you need a way to process that data. And it was not possible up until now. So the recent work that me and Peter Barker and Randy all together have done is that we have converted this mini fence to a spherish shape like this. So if you can recall, I told you that if we have like 5 obstacles, one is here, the other one is a little further away. We pick out the closest distance. The same idea has been extended to 3D. So so this is one, we call this faces. So before we used to call it sector because it was like a 2D kind of thing, but now we call it a face because it's more 3D. So this face right here. So we could have 100 distances along this face, and we'll just pick out whichever is the closest distance in each face. So we have 5 layers of these faces, from top to bottom. So there's one in the middle, there's one in the bottom, there's one between middle and bottom. So there are 5 different faces that we have. So before we only had the ability to store 8 obstacles at the end of the day, but now that has been transformed into 40 obstacles, which is all around the vehicle, right? It is 3D. And just to give you a visualization of how this works. So this is a tiny tool that I have built to, not a lot of people understand the visualization of these mini fences that we make. And this is a tool that is still sitting in a local branch, and I intend to push it up to master so that other people can also test it. I have not really found a good way to do it yet, because this was a really hacky way that I figured out. So on the left screen, you'll see the normal civil view. And the green fence is actually an obstacle. It is treated as a proximity obstacle. So this is at the default state, right? There's no obstacle detected, and this is how the fence is. But you realize as soon as I give the command of go forward, I push the sticks forward on loiter, you'll see that the fence starts coming in together. And that is basically how, so before, in 2020, we only had this middle sector, this middle layer right here, the middle one. But now we have these 5 fantastic layers that helps us, get 3D. And, they're going in together. And that's because at this stage, you'll see the vehicle is actually quite near to the obstacle. And so this is the view that the humans see, right? This map right here. But this is what the vehicle sees. This is what the proximity libraries see. This is what the avoidance libraries see. And if I was to rotate, since this is body frame, if I was to rotate this, rotate the vehicle, the points switch, like the different points come together, but the circles themselves don't rotate, because this is very much body frame. This is not earth frame. And if I was to bring back the vehicle to its original position, then you'd see that the fence points again. This is again what the avoidance libraries is seeing, and this is happening. This visualization is happening in ArduPilot. I mean, the graph is being built in a Python script outside, but all of this is being built inside the proximity library. So this is the most significant change that we have brought about in 2021 in the proximity libraries. And this has been merged to master, and I'm really excited for Copter 4.1, Rover 4.1 release that are going to be able to use this. Apart from that, there is now a filter on each of the face. So what happens was, so we had a bunch of users complaining. For example, SF40C, 95% of the times the data was fine. But what happened was that there was this one awful second where the distance would jump from 10 meters to like 0.5 meters. And that's a nightmare for avoidance, right? Because if it's seeing an obstacle at 10 meters and all of a sudden the sensor reports obstacle at 0.5 meters, it's going to react to it, right? And we had no filters available. So what I did was I added a low pass filter, which adds a basic degree of smoothness as well to the data. And the cutoff filter to that, the cutoff frequency to that filter is very much customizable by a user settable parameter. So I'm also, I'm hoping that any noise that people were attaching, random rangefinders from different companies and seeing their raw noisy data. And this is just a good way of, making sure that connect whatever sensor you have to ArduPilot, but we've got the noise covered. You don't need to worry about the copter going crazy mid flight, just because a sunlight came for a split second inside the sensor's view. And another sort of nightmare that we face with avoidance is ground detection. So copter doesn't know where, if the ground is an obstacle, or if it's just ground, and you need to ignore it. There is no way of knowing. And so what happens is that when you're taking off, it sees the ground below. The lidar, they see the ground below or the grass as obstacle, and it immediately reacts to it. Which is scary because you're so low that any reaction could lead to a crash. So we have implemented this very elementary ground detection inside Proximity Library, which uses the downward facing rangefinder, and it tries to filter out any the 3D point that is on the ground. So for example, the downward facing rangefinder is reporting 2 meters altitude, and we feed in an obstacle which is also 2 meters below. So we immediately know, this is a point that we need to filter out. This is the ground, just ignore it. And this again is we can disable it if we want to. Users are not forced to use this, but if you're someone who is having troubles with ground, make sure that you try this new feature in Copter 4.1. It is of course not a feature in Rover because it doesn't make sense there. Right. So what's missing? We've done a lot of work in the proximity drivers, like a lot of it, but there's still some stuff missing. So the first one being that we've not really received a lot of support queries on, but I'm sure someday they'll come when avoidance is a little bit more being used. So we only support one type of proximity sensor at a time. So you can't connect, say, two Lightwear SF 40Cs or 45Bs, or you can use 8 rangefinders, but that's a different thing. You can connect 8 rangefinders at the same time, and proximity libraries will, they will support that. But as far as proximity drivers, proximity sensors go, you can only use those 8 rangefinders. Then you can't connect a SF40C with it. So that's one limitation of the proximity libraries. Now, the other thing is that the rangefinders, if you go see the rangefinder orientation parameters, it is defined to it is limited to 8 orientations. Yaw 45, yaw 90, yaw 180. It is only limited to those orientations, and as well as upward and downward facing rangefinders. But now, since we have a 3D boundary, like what I showed you just a minute back, we can actually extend the rangefinder orientations to be much more. And I don't think this is a big deal. I most likely already have a basic working PR, but with a little bit more testing, I'm sure that we can get this done. Apart from that, we don't really have good settle testing abilities with proximity library. So this, for example, I was forced to make this visualization, but it took quite some time to make this visualization actually. So it'd be great. And settle being 2D in itself, it's kind of tough to have 3D testing abilities purely settle wise. And how do we get around this, and how do we use other 3D simulators? That is towards the end of the talk. But yeah, so better settle testing abilities obviously is, and auto test is something that is missing. And another problem is this boundary is not closed. So this boundary right here, this boundary that you see, it has 5 layers, but it does not have a pitch 90 and a pitch minus 90 layer. So it is very much open from the top and bottom. So if right now, if you were to try to feed obstacle that is pointing upwards, it is going to put it on this layer, the topmost layer. It is not going to have this. It's not going to have a point directly upwards, which is also something that I have been intending to work on, but haven't found the time yet. So any questions regarding proximity library? All right. So moving on to simple avoidance. Right. So the proximity library is like a stepping stone for simple avoidance, right? And simple avoidance is the type of avoidance that we use in manually controlled flight mode like loiter. So not a lot of people know how. A lot of people have used simple avoidance, but not a lot of people know how simple avoidance works. So we have two modes inside simple avoidance. One is the slide mode, and one is the brake mode. The brake mode basically just stops in front of the vehicle, which is not really that complicated. But sorry, it just stops in front of the obstacle, which is not that complicated. But the slide mode, what it tries to do is it tries to slide around an obstacle. And the way that it works is quite simple, actually. So we have a velocity vector, right? This is the velocity that is being fed by the loiter controller. And we try and detect, we have these obstacles coming in from the proximity library. And we try and detect, how much of what component of this velocity vector is towards this obstacle. That we basically project this vector onto this obstacle vector. And this is the drone right here. And then if we find out that it is getting quite close to this obstacle right here, we try to shorten this vector towards the obstacle. So the projection of this vector towards this obstacle, we try to shorten it, and then we add it back into the velocity vector, and the result is something like this, right? So if you were going straight ahead, instead of going straight ahead, now you're going to have the tendency to slightly bend to the left or the right. The very obvious problem with this method is that number one, if you are directly, if you're perpendicular to the obstacle, the projection is also going to be in the same line. So you just end up shortening your velocity vector and not actually, changing directions. So if you're, going straight to a wall, you're not going to go left or right. You're just going to stop right in the middle. But if that wall is, slightly tilted, or if the vehicle's direction is slightly, oblique towards the wall, then we're going to have a smooth sliding feature that we support. And the biggest problem that we had in simple avoidance till 2020 was that it can stop in front of the vehicle. It can stop in front of the obstacle. It can slide around the obstacle. But if the obstacle was to come closer to the vehicle will not go back. So we didn't have an active avoidance feature per se. We just had a detect and stop feature. But now in 2021, we can actually maintain set distance from the obstacles. So this was a feature that I developed back in my GSOC times. It was one of the highlights of my work. And what we do is that we could have obstacles. It's not as easy as it seems, because we can have obstacles from all directions. So we can have obstacles from the front, we can have obstacles from the back, and if we are backing up, we have to make sure that we don't back into an obstacle. So this has I won't get into details of it, but this has a slightly it just calculates a vector which is free from all the obstacles, and it bang in the opposite direction of all the obstacles. And so this was a very interesting simulation scenario that I developed using Morse. So Morse Simulator is an excellent platform to test avoidance related stuff, because we have a good support for it. And unfortunately, Morse is now dead, and it's not being developed by it's not being actively developed. But just using the last Morse version is fantastic. So you'll see in a minute. So I call this simulation the choke room, and I love it because we have walls from all sides that are diverging into the copter. And you'll see just in a minute that, so this is in loiter mode, right, with simple avoidance, and walls are approaching from all directions. And you'll see how we back away. And this is the new feature that we are releasing in Copter 4.1. And if a user was to do this in Copter 4.0, it's just going to collide into the walls. It's going to stop right in front of it, but then when the walls come closer, it's going to collide. Similarly, just approach it from any direction, anywhere, and your copter is safe. It's going to try and maintain, as much of a margin as possible. So that's about backing away, and the biggest feature of simple avoidance probably that we have. Apart from that, simple avoidance is now smoother and safer. So when I started experimenting with avoidance, and a lot of people on the discussion forums as well, actually, they used to report that the vehicle is very aggressive, the vehicle is twitchy, and which is not a good thing, right? Because if you're trusting your vehicle to not collide into something, especially beyond visual range flights or FPV flights, you don't want vehicle to be twitching when you're avoiding obstacles. That's just eyesore. And so I investigated the reason of why this was happening. And this graph actually pretty much explains the reason of those twitches. So we have the input velocity, and then which is coming from loiter, and we have an output velocity which is coming from the avoidance libraries. And what happens is that the difference between the input and the output velocity, which is basically the acceleration demanded by the avoidance libraries, it reached hundreds of millisecond second, which meters second, which was just crazy, right? I mean, vehicle can't accelerate that much. And so what I did was we have this new feature called we have this new parameter which can actually limit this acceleration to, so this is right now limited to 2 meters per second squared. And this is what the avoidance code actually demanded at first. So just to give a demonstration of what used to happen and what happens now with this new bit feature. If the vehicle was traveling fast, it used to react this aggressively, and you'll see that it starts. So this is the this is the obstacle right here, which is this will never happen in real flight. I hope that there's an obstacle 10 centimeters away from the vehicle, but you'll see that the vehicle is just swinging around, and it's not a controlled backing away. It's just going crazy, as you can see. And that no one's going to be trusting their vehicle with avoidance if this is what it's doing, right? So to fix this, as I said before, we have this acceleration limitation code, and yeah. So just have a look at what it does now. So it's flying, quite fast, and my hand comes, and there it is. And you'll see the velocity being, gradually decrease instead of, having a sharp decline in it. And the acceleration is very much limited. And just once more, if you see the vehicle going straight forward, and my hand comes in between, it stops gradually and it goes back. So yeah, this makes the flight much smoother. And if you see on the top corner, this was the expected acceleration. And the expected acceleration, this is the kind of stuff that we were demanding out of the vehicle. 500,000. I mean, that's just crazy. We can't do that. So all of this is now being limited, and the result can be seen. Right. And one of the other biggest changes to simple avoidance is that it is now 3D, because we have 3D data that is coming from proximity sensors. So, and we have the ability to store 3D data. So of course, you're going to see a lot of this now 3D, because that's pretty much what I've been doing since the past year, converting everything to 3D. Um, yeah, this particular test is with a D455, which is which is stereo depth camera that I introduced a few slides back. And this is a test of it flying. And I also want to take a moment here to thank my main sponsors for this work, which was Harris Aerial. They provided all the funds and all the equipment, all the funds that are needed for the equipment. So it would not have been possible without them. So thanks to Harris Aerial. Right. So just to explain you what is going on here, we have this FPV view of the camera. So this is a tripod on the left with a surface mounted camera. On the right you see a FPV view. On top of that RGB FPV view is a filtered depth camera view. So this is filtered. Okay, this is not the raw depth that is coming from the camera. The raw depth visualization that is coming from the camera is on the left, on the top, in the top left. So again, crazy on how much data we are processing and how much data we have. Right. So you'll see the vehicle approaches me, and just have a look. So as soon as I start approaching the vehicle, it moves back, and so that's the minimum it can do. But what's more interesting to see is that if I approach it from below, then it's going to actually climb up. So it's very, very slight now, but you can see that the vehicle is actually climbing up instead of going back, because that's where this was a user commanded movement, by the way. And yeah, just in a moment you'll see that the vehicle will actually attempt to climb up instead of going back. And this is also a recent change that we have done. Yeah. So as you can see, it's pretty smooth, and with all this data, it's a much safer flight now, and it's all working great. So right. So that was just with one camera, right? And that was just with that limited amount of data that we are receiving from one camera. But now, with all the work that has been put into by Peter Barker, by myself, and by Randy, we can actually have multiple depth cameras that are attached to the vehicle, and to have like a almost 360-degree view of the vehicle. And again, all this work was sponsored by Harris Aerial and QPilot. QPilot actually, donated me the vehicle required for, because all these cameras are heavy, all the companion computers are heavy, and I needed a much bigger vehicle. So QPilot was happy in providing me that vehicle, and all this would not have been possible without them. So thanks to QPilot. Right. So this is the setup that I've used for this interesting use case. So we have two cameras. If you notice, there is one camera at the front. This is the D455. And there's one camera at the back, which is the D435i. And we have the Jetson Nano. So the earlier versions that you had saw, that they were using the Intel up squared. But since then, I have you started using Jetson Nano. And this is a Hexoon TD650 frame. And so it's a really interesting thing, interesting setup that I have here. And so, just a wide, very, very wide view of, what all is here. And so this is the front camera, the D455, and this is obstacle number one, the garden umbrella there. Obstacle number two is me right here, holding the stick. And on the back there is a D435i, and that's detecting obstacle number two. And so you just see the massive amount of data that we are processing, and that is being fed into the vehicle. And so the frames per second on this that I was getting out of the two cameras was a little below 10 frames per second, because the Jetson Nano can't really keep up with, it's not good with multi-camera support. If you had just one camera, you'll get 15, 16 frames per second, but which is sufficient. But with two cameras, it was lagging. I think, if I upgrade to a better Jetson computer, like a more expensive one, like the TX2 perhaps, then it's going to be slightly better. But for a demonstration, this works. So and you'll see in a moment that I approach the vehicle from behind, and the copter reacts to it, right? And it stops right in front of the obstacle, the other obstacle. And so no matter what I do, it's not going to collide into it. It's going to go left, right, but it's not going to collide into it. So I'll just let the video play and just tell you what exactly is happening. You can go up, you can go down, which was earlier not possible with 2D lidars, right? But it's not going to, yeah. So obstacles on both sides, but now you're going to see that it's going to attempt to go to left instead of going straight. So yeah, that is just amazing ability, right? That uh, the vehicle will refuse to collide into any obstacle no matter what you do. And the avoidance, another thing to notice is that avoidance is mostly smooth. It's not twitching around. It's not reacting aggressively either. So on most parts, it should help the users avoid obstacles and not really be a gimmicky feature. Another just cool demo in the same video is just a second. Right. So right now you'll see that just this one camera set up on the left and the copter flying. So I'm pushing on the sticks. If you see, I'm pushing as far possible as I can, and this is loiter mode. And the vehicle is just still there. It's just standing steady. It's not doing anything, and which is amazing, right? You can go left, you can go right, but it will not let you go forward. And you can approach it from any direction, up or down, as long as it's in the camera's frame. It's not going to let you collide into it. So that's just, I mean, it's just self-explanatory how this can be used, right? So that was it about simple avoidance and how much we have upgraded it in this year. And uh, we have a couple of tiny features as well that I've not mentioned, but uh, so we have this huge issue of detecting ground as obstacle, and I already told you that in proximity avoidance, sorry, in the proximity library section. But so to counter that problem, we also have this new parameter which you can set up, which basically says that do you want a minimum altitude before avoidance is switched on? And if you're below that altitude, then avoidance is automatically turned off, and so you don't react to the ground. And another thing that is to do is to make slide more slidey. To it does slide, but we want to make it a little bit more than that. The slide should be more obvious. And obviously, we can't say that it is 100% reliable or 100% smooth. Those improvements will keep on going forward as time progresses. A real cool video of so I'm working a lot on ground detection. So a really cool video of how we can do it outside of ArduPilot, how we can do it at the companion computer level. Is So yeah, so again, this depth visualization and this RGB camera view. But this time, if you see on the depth view, we have these tiny circles, and these tiny circles is actually land. It's the land that is detected. So if you see when the video unfreezes, yeah. So it's tracking the land pretty well, right? And I'm flying quite low, but if you notice, there are no red. There's this red distances here, as I told you before, but there are no red distances here because it is not detecting any valid distances, and that is because we have land here. So yeah, so you can do all sorts of crazy. And this algorithm, by the way, it's a very simple algorithm called ransack. Many of you might know. I can, if I start explaining the algorithm, we'll go over time. So I'll skip the algorithm description. Uh, But yeah, so you see how low the vehicle is flying right now. It's barely a meter above the ground, but the land is being detected, and it's not reporting any obstacle. So that's just a great thing to have. And this feature does not exist yet in the scripts that we provide. But I'm hopeful that in the very near future I'm able to have this feature as well. And so when an obstacle does come in between, and there is land, so that's the obstacle. You'll see that the obstacle is being detected and the black dots move away. So that's also a good handy feature to have. And this makes it like super reliable. So you have ground detection filters here, you have ground detection filters in proximity library, you have ground detection filters in avoidance, and all three of them together, you can be almost sure that ground is not going to play any role in low altitude flying. So yeah, that was it about simple avoidance and manual mode avoidance. The rest of the presentation is going to be about obstacle of path planning and autonomous in autonomous mode. So any questions so far? Right. So I'm audible, right? My mic is working fine.
Yes, it's just
Yeah.
No problem.
it's quite incredible. I mean, it's the question, but so much as an observation. I remember Peter brought a vehicle running your code out to Spring Valley for us to try it. It was just to experience it directly was quite incredible. To watch it doing that avoidance, it was really quite stunning how well it works. And it's the sort of thing where I would love the conference to be in person and we actually have people experiencing just how well this stuff works. But yeah, very, very impressive. But I should let you get on with the next section.
Right. Yeah, I'm going to go quickly because we're running out of time. So and yeah, just
we
one
can go
last
a few
thing.
minutes over. Don't need to rush.
Yeah, thank you. So just one more thing before I wrap up this section. We are also actively working towards, and Peter Parker does more work in this, but on making really easy AP sync images out of this. So all you have to do is just connect everything and you're ready to go. So we are constantly working towards that. But this new development features, they take a little bit time to reach that section. So if you are a developer and you're interested in this, then you can ping me anytime. I'll send you my scripts. You can try it out, and that'd be great. So next, moving on to the autonomous modes. So we have something called as the obstacle database, and this is needed for storing obstacles. So what this does is that it stores obstacle inside ArduPilot, inside the flight controller's memory, and that data is being constantly refreshed. And these obstacles, they are stored as earth frame vectors instead of body frame vectors. And the reason is obviously that we want to have some sort of memory with respect to obstacles. So for example, if you have a 1D rangefinder and it's yawing towards the right and it sees obstacles behind it, just because you have yawed a little bit does not mean that the obstacle is not there. So you want to have some sort of memory, right? So that's what the obstacle database does. And so it's a really, I love the implementation of how this was not implemented by me, it was implemented by someone else, but it's really great how it works. And um, so the recent updates that we have brought about to obstacle database is that it is also 3D now. So it used to only store XY, but as like a vector from origin, but now it stores XYZ, which is really great, right? And we also have the ability to reject obstacles around home, and this was also just a very simple feature to remove the ground that was being detected, right? Again, just adding on to that. So while we are taking off and landing, which is mostly around home, you can reject obstacles in the obstacle database. You can choose to use this. You can disable it with the parameter up to you. So bendy ruler. So the obstacle databases, the obstacle database directly feeds into bendy ruler, and bendy ruler uses that those proximity data and for planning its path. So bendy ruler was actually algorithm that was the original work of Canberra UAV and Tridge and other people worked on it. It was first implemented for plane. It was not at all for rover and copter, but now it is only being used with copter and rover. And I think there are plans to have a Lua script for plane, but that has not yet been implemented. And so it is a relatively simple ray based algorithm. And you can so Randy also explained this explained how this works in in last year's conference, so you can have a look at that as well. But just to give you a little background, what it does is it does avoidance in two steps. Step number one is that it sees there is an obstacle in front, and so this red marker right here, this is the obstacle in front. It projects distance a little bit forward, and it sees, oh no, this is quite close to the obstacle, we can't go in this direction. So it turns a little bit to the left, 5 degrees to the left, and it sees, okay, no, we still don't have proper distance to, we don't have a set margin from the obstacle. So and then we turn right. And so so it just does this ping pong left right maneuvers, left right not maneuvers, but left right location projections, till it figures out a position which is this green line here, that is free from the obstacle. And at this point, we could stop this algorithm here and we could just go forward. But what this algorithm does is it does a step two, which is that it does the same search, but in front of it, from this already projected point, so that we are sure that once we reach this obstacle, once we reach this deviated point, there is no obstacle in front of it. I hope that was clear. So and this path, so we have two path planning parallel. We have bendy ruler and we have Dijkstra. This works with proximity sensors. So if a human starts walking towards it, or if a car starts running towards the vehicle is going to be able to avoid it. The same is not true for Dijkstra. So just a demonstration of how well this is working in 2021. uh, so this is just a copter, going up, going to a zigzag sort of pattern, like back and forth pattern. And I usually, have a slow moving vehicle, so that if anything goes wrong, I'm able to control it. But it can be much faster than this. So now you'll see a wild obstacle appears out of nowhere, and as soon as the vehicle turns around and it sees the obstacle, it moves towards the left and it avoids it. And this is all purely bendy ruler, by the way. I'm not doing anything. I have the controller in hand, but it's not being used. It's just so that if it goes too much to the left or too much to the right and it collides with the where the sensor can't see, then we have a problem. So yeah, and it's just great how bendy ruler works. So that's about bendy ruler, and you can approach it from any direction, and it's just going to continue towards its path as soon as the obstacle is clear. Right. So moving on. So what are the updates to bendy ruler in 2021? The updates are that obstacle detection is now 3D, but this does not imply that the algorithm is 3D. So the algorithm is very much 2D, and it only searches, in XY direction, or as I inbuilt. It's not a tough thing to do, but it's just that we have not gotten to it yet. And so with this feature right here, where the obstacle detection is 3D, you'll realize that when the vehicle is pitching downwards, and if it's rolling around, it might detect the ground, or it might detect an obstacle which is down below. But back in Copter 4.0, this was detected as something which is at the horizontal level. It wasn't detected as an obstacle down below. So now what we do is we multiply the obstacles with a rotation matrix, the attitude of the flight. And so the difference that it makes is that in these this is again Morse, and this is this is Copter 4.0 on the left, and this is Copter 4.1 on the right. And you'll see is that the vehicle keeps avoiding random obstacles which were actually down below and not in front of it. But the vehicle on the right is traveling smoothly. It has no problem at all. And this is a low altitude flight. It's like 2-3 meters. And uh, just a second. So yeah, you'll see, that this one has already reached waypoint 3, but this one's struggling to even cross waypoint 2. And you'll just realize that the copter in the end, because of such false, it not detecting those false obstacles, reaching the final state early, quite earlier than the copter 4.0 version. So that's one update to Bendy Ruler. The other update is performance improvements. So the problem with Bendy Ruler was that it was too it used to be, it was too easy for it to change the directions. So if it is heading towards the left, and all of a sudden it finds that the path to the right is just a tiny bit better, like just minuscule bit better, it used to immediately switch over to it. There was no restriction on the how much path can be changed, which is not a good thing, right? So you'll see why it's not a good thing. So the vehicle is heading forward, and both of them react identically. The one on the left is again copter 4.0, and the one on the right is copter 4.1. And you'll see that the vehicle, they're both traveling, everything's fine till about this point. But all of a sudden, the one on the left, it started going towards the opposite direction. But the one on the right, it is sticks to that pattern, and it doesn't deviate back. So, and you'll realize that this vehicle is now stuck. You can't. So if you were to do this in copter 4.0, it's just going left, right, and you won't be able to get out of it. But now you can, we hopefully have more resistance in path change, and that leads to just more robustness in this algorithm. So that's another change that we have bought in 2021. And so to do this, we have a couple of parameters actually, and I'm going to have a lot of documentation on, which is still left to do, but on how to do this. We also have a new bendy ruler type. So instead of going horizontally, for people who prefer the vehicle to go vertical, we can do that as well. So the vehicle is again flying back and forth, back and forth. This is tiny. I hope you can see the tiny copter that is going back and forth. And right. So as soon as an obstacle appears, uh, you'd see that the vehicle actually goes up instead of going left and right. So just in a second you'll see that. Yeah. So it climbs up, and it dodges the person, and it climbs down and resumes to its original path. So if you're in, say, a farm or somewhere where there are low plants below you, or just if you prefer climbing up, then this is the feature to go with. And basic difference between this and the horizontal bendy ruler is that it just searches for free path vertically instead of horizontally. That's the only difference. Yeah, so that was it about bendy ruler, and what are the updates to bendy ruler. Now moving on to the other type of path planner, which is Dijkstra. So I'm not gonna explain how Dijkstra works, and I think Randy did it in his last conference. But just to give you a little idea, Dijkstra is a very famous algorithm that is taught to almost all math majors, all CS computer science majors, and if we have a set of nodes, it helps us calculate the least, the shortest distance path through them. It's a graph based algorithm, and it's just very famous. You can read about it on Wikipedia. We have multiple YouTube videos, and so we have that as well in ArduPilot. And but this does not work with proximity sensors, and I'll tell you why in a while. So the way this works is that we have this fence. This black line is fence, and it marks these safe. It creates these nodes, these red dots, these safe nodes, and it plans a path through them. So this is the shortest distance through the nodes, and that's basically how Dijkstra works. Uh, so yeah, just a second. Yeah, a new addition As I said, that Dijkstra's does not really have the ability to detect proximity based obstacles. But the reason is that Dijkstra's takes a long time to process, and even for a small obstacle, usually the tendency is that the obstacle database, it stores 50, 60 different points inside it. And so we'll have 50, 60 different nodes, and then and this keeps changing, so the Dijkstra's algorithm will have to rerun again and again and again, and that's just something that most computers can't keep up with. So that's the reason why Dijkstra's does not really have proximity sensor detection. So to just to still use Dijkstra's, and to have the bendy ruler capabilities, we have come up with the bendy ruler and Dijkstra fusion. So we use, so this is sort of like a ROS way to a robotic operating system way to do this. So we have Dijkstra's as a global planner, which basically at the start of the mission, what it does is that it plans a path, that this is the general direction that we're going to go towards. And if we have a few obstacles in between, that is bendy ruler job. We're going to switch over to bendy ruler, is going to take care of all these obstacles. And as soon as all the physical obstacles, the proximity based obstacles are done, it's going to switch over back to Dijkstra's navigation. So now users don't have to choose, do we want bendy ruler or do we want Dijkstra? We want Dijkstra, but we can't use, it doesn't have proximity based avoidance. So now choose this, which is going to be available in Copter 4.1 and Rover 4.1. And just a simple demonstration on how it is much easier to demonstrate this on a simulation rather than real flight video. So I have this, the vehicle is in guided mode, and the vehicle is down all the way here, and I have asked it to go here. So the green line here is the fence, right? And there are proximity obstacles as well. So it has decided to go around the fence. That's all Dijkstra. And on the top also you'll see Dijkstra is being printed, because that's the OA type that we are using right now. And as soon as the vehicle approaches the obstacle, it switches over to bendy ruler, and now it's going to so it's deviated from the path, as you'll see on the bottom right corner. And it's the only thing that is doing right now is avoiding this obstacle right here. And as soon as this obstacle is avoided, it's going to switch back to Dijkstra. So in a second, you'll see the map right here, and right there, you'll see that the path is all of a sudden, the Dijkstra's path is calculated, and it has switched back to Dijkstra's maneuver. And it's just going, now it's the shortest path again. So you're covered in all ways. So this is again the newest path planner feature that we have. And what's left to do. So again, the obstacle detection is 3D, but bendy ruler itself is not 3D. It's very much 2D. So do that. We can integrate simple avoidance in our autonomous modes as well. So that PR exists for this. I've done it. It just needs a little bit more testing. So most likely 4.1 is going to have this in next couple of weeks. Spline navigation, to the best of my knowledge, does not work with the path planning algorithms, unless that has changed in S curves. I'm not aware of. But up until at least last week, spline navigation, if you were to use spline navigation, it's just going to collide into the obstacle. So that's something that we need to do. And yeah, Dijkstra does not support proximity avoidance, but I explained, that's probably for the best. So this is the very last part of my, last couple of slides, and I'm almost done. Sorry for taking more time than I was allotted with. So this is just for those simulation geeks that love simulations. And as I said before, simulation is kind of tough in this area. And back when I was a noob, and I did not know how all of this works, I used to just test everything on flight. And I have had scripts crashing down, and that causing the blades to cut into my hand and stuff like that. So several body parts have been injured in the process. I'm not lying, and I'm sure same is the case with everyone else. So we have two excellent simulators that are really easy to use. thanks to people like Tridge and Rajat and all the people who have worked on AirSim and Mars. These are excellent platforms that you can use in combination to sit in to test everything before you take flight. I hope you remember, the land detection code that the ransack algorithm that I showed to you a while back. Before I tested it on flight, I actually coded the same thing on AirSim. So this is how it looks on AirSim, right? This is the depth view. It's the exact same. It's the D435i simulated in AirSim, and this is the the RGB view. This is the depth camera view, and you'll see that the land is being detected with those black arrows, and I didn't even need to change any code. I just copied it as it is from this to the real sense cameras. It was that easy for me. I didn't need to change anything. So you'll see how well these simulators actually work and how incredible it is to use them. You can have all these blocks, and so you can take it to crazy things like flying just half a meter above the ground and see if your algorithm is robust enough to detect obstacles there. And so as you'll realize that my algorithm right now is working quite nice, and as soon as the obstacle approaches, it's going to detect it, and it's going to stop. So that's how incredible AirSim is, and I'm going to have a lot more documentation on how to set up this sort of stuff with AirSim. If you're someone who wants to do multi-camera simulation, multi-depth camera simulation with AirSim, so this is the one on the left is a forward-facing depth camera. The one on the right is a backward-facing depth camera, and one on the top is a bottom-facing depth camera. And so you can do and just see the amount of details that AirSim gives us. It's as good as testing physically, and it's again divided into those 3x3 grid that I was talking about earlier, and just see how detailed the simulators really are. And when it starts approaching, you can see the trees, and you can do any sort of ML AI stuff that you want to do, or any statistical analysis you want to do. You can do it right here. You don't need to take the copter out anymore. And if you want to, so this is again something that I really want to work on the future, that have the camera pointed downwards and be able to detect terrain much before the copter is up on top of it, right? So right now we have a downward facing rangefinder, and when the vehicle is on top of that terrain, that's when we actually figure out where the if you have to climb or descend. But we can actually plan for it in much more future if you use these cameras. So yeah, so as you'll see, if I pause it right here, this is the downward facing, this is how the trees look from the top, and this is how the trees look from the forward. And it's just crazy on how much how you don't even need to get out of your seat anymore, and how you can just use these simulators. So yeah, and then there's Morse, which I've already showed you a few videos of, with the choke room and stuff like that. So that was it regarding my presentation, and hopefully you guys had had fun looking at all the experiments that I did. And yeah, stay safe and fly safer. And apart from that, I just want to give a shout out to all the people that I've worked with, Randy, Peter, who have been really mentoring me. It's just been a year. It's just been a year since I've been with involved with you guys, and it's just been transforming on how much I've learned. So thank you, and that's it from my side.
Fantastic. That was absolutely brilliant, Rishabh. Really enjoyable. And it's incredible the progress that's been made over the last year on object avoidance, and it's great to see that the simulation systems being used in such a marvelous way. So really gladdens my heart to see all this stuff coming together so well with such sophisticated capabilities. So are there any questions off the floor?
Hey, Tridge, this is Bill.
Yeah, g'day, Bill.
Hey, Rishabh, this is great work. I really loved watching your presentation, and really great capabilities that have been brought to to ArduPilot. But the question for you is, what hardware do we need? I mean, so the depth cameras, it seemed like you had some sort of a companion computer or something like that doing calculations. Right. Or so I guess describe real briefly kind of with depth camera, what do you need? And then with like, I guess there's the 3D, or not 3D, but basically the range finders. I guess which one of those require companion computers?
Right. So all the yeah, thanks for this question. And so the really easy answer to this is that all the sensors that we support directly in copter. So those are the lightware sensors, or the range finders. Those are all directly connected to the flight controller, and so you don't really need any companion computer with that. You'll get this exact same, all the exact same output without any need of companion computers. You just need to set the right parameters and you're good to go. It's that easy. But with these cameras, with these 3D cameras, so it is important to know that all of the calculations actually happen inside the vehicle, inside the flight controller, and the only usage of the companion computer is to connect to the cameras, extract the depth image, and just basically divide it into a 3 by 3 grid, and in whatever way, and pack it into a XYZ obstacle and send it as a mapping message. So that's the only use of the companion board. But all the calculations, all the avoidance, all the 3D spheres stuff that I was showing you before, everything's done on board.
Okay, thank you.
Anything, if I can answer any other questions.
Yeah, I've got, well, first up, on behalf of all the other developers, we all hope you healed up quickly as you were developing everything. And how have you gone with, you look like you've got a lot of USB 3 sort of floating around there. How much trouble have you had sort of, dealing with interference and that sort of stuff? And is there a way of sort of doing it without using, those painful things?
As you said, the multi-camera support, when you have more than one camera, it's really it's a pain in the head to have all those cables and all those USB 3, and these, by the way, require USB 3.0 ports. As much, so I have only tested with two cameras because I only have two cameras, and it's not been a issue so far. But as I read on the forums, and so I spent like hours scrolling through forums, figuring out what the problems I have and if other people have it. So what people tell me is that beyond, at least on the Jetson Nano, so if you have a high powered laptop like I use, it's not going to be an issue. You can use a USB extension hub, and you can connect as many cameras, like 5, 6, 8. I've seen people use 8 cameras at a time, and it's not really an issue. But with a low-powered flight controller, a low-powered companion board like the Jetson Nano, anything more than like 2 cameras, you're not only going to reach the limit of how, if you can on the CPU limits, but you're also going to reach the bandwidth limit of the USB ports. So anything more than two or three cameras on the Jetson Nano is not advisable at the moment. But if for high-powered companion boards, you can easily go to 4. A lot of people have done 4. But there is no way we can circumvent that at the moment. You can have multiple companion boards if you want, but that's not a solution, right? So sorry, no solution for that.
Is there any opportunity to work with work with the cameras themselves to output just the data we need for the autopilot?
So I have asked Intel about this in one of the forums, and they said that this is something that they want to do, which will be really interesting. So you can have like just a tiny camera, and a few cameras actually do this. The Intel the depth cameras that I have used don't do this, but that is very much a possibility in the future. Companies are working on it, but we don't have a product yet that does this. And when that happens, we won't really need any companion computer, right? We just need Mavling messages being transformed from the camera directly to the vehicle, and all works well.
Thanks, Matt. Great work.
Thank you. Is there anything else I can answer?
There's one from YouTube, mate, just from Scott Arrow. If the
Right.
if the obstacle is suddenly removed, do you get full stick input immediately, or does the controller slowly add in all the stick input?
Yeah, this is a very good question. So right now, this is a problem with Copter, that if the obstacle is removed all of a second, it does have the tendency to give a bit of a jerky reaction. So while the obstacle comes in front of it is not an issue, but if the obstacle is removed, it is a slight issue. But this is something that I'm working on, and this is something that I noticed just past week. So I'm sure that in the next month or so, we're going to have a solution for this as well. But it is a problem right now.
Cool.
All right, fantastic. So
Yeah,
no further questions? Randy?
No, I was just saying, just really, really great work. And, working over the last, year or a little bit more with Rishabh, what I really always appreciate is just the level of testing that he does. So, there's no point in having a obstacle avoidance system that, isn't reliable, but he just puts so much effort into the testing to make sure that it really works. It's
Randy and I've kind of been lucky enough to see this sort of presentation on kind of a weekly basis for quite some time, which has been absolutely fantastic.
Thank you. Thank you so much, guys. And it would obviously not be possible with without the mentors like I've gotten. And just last line that I just hope that avoidance is not a gimmicky feature anymore, and it is something that we use compulsorily in all vehicles, and people actually start testing it and start realizing that it is reliable, and they can use this in their everyday vehicles as a fail-safe feature, and not as something that they shoot a video and then they turn it off. So I'd love to hear reviews of people, of developer team members who flash 4.1 and start testing them. And if there are any, we have changed so much, like we have added so many new features that we're bound to have bugs. But I'm going to be all on top of it and hopefully fix it as soon as possible.
Fantastic. Thank you so much. All right. Well, that ends the evening's presentation for the second session of the 2021 Dev Conference. And thank you very much for the two presentations we had this evening. So we're back tomorrow morning, Canberra time, which is probably for many of you going to, if you're in Europe, will be the middle of the night. My apologies for that. So we're starting off bright and early with at 9 o'clock in the morning, Canberra time, with Tom Pittenger giving an AP Perif update, followed by Julio Mendoza about ArduPilot in Latin American research, and then documentation update and the ANU visual odometry system. Then finally, the blimp support from Michelle. So really looking forward to those talks in the morning. And so thank you all for attending this evening, and thank you everyone who joined us via the live stream on YouTube. And so wish you all a great evening and look forward to talking to you all in the morning. Good night, everyone.
Catch you later.
Thanks, Tridge. Good night.
Hey, everybody. Good night.
Cheers.
Bye-bye.